So, all the interesting things there are to see. And that mainly comes in when we have fraction powers of x, our last type of function. Now, to keep it as simple as possible, for the first time you see this, I'm going to look at just one term, and I'm going to look at x to the 1/3. Now, I can write it as x to the 1/3 or cube root of x, of course, and you should see that this is defined everywhere. It's defined for all x. It's not the square root. Cube root's defined everywhere. Cube root of anything you can find. So I don't have any asymptotes. No asymptotes or anything. So out of step 2, really nothing is coming. Not much. Okay, so let us see, what does the derivative tell me? Well, for the derivative, I'm not going to use the root version. I'm going to use this version because I can then directly apply the power rule. So it's going to be 1/3 x to the negative 2/3. Now I don't want to look at this version. I liked it for the power rule and for nothing else. So I want to maybe leave the third in front, then move it so I don't see a negative power of x. And perhaps you like the root version moving forward. Always know that it's an option, like so. And I do like the root version for anything other than derivatives. And I'm done with the derivative now. I had a reason to clean this up because I need to now see, where is this function equal to 0? Where is this function, the derivative, undefined? So there's no benefit right now to make the fraction power of x function complicated. Let's just look, this is in that type. Let's just look at a simple one that we can quickly do. Where is this derivative equal to 0? Is the question for you. Have you learned from the previous example? Or every example is teaching me something, actually a bunch of things. Where is this derivative function equal to 0? For which x values? None. You're saying nothing? It's none. You're right. Never. Again, not 0. But it's good that you're saying this so that you can learn. If we don't say something, even if it's wrong, we're not going to learn. It doesn't stick. By making mistakes, you remember it way better. It's way better. When the only things that can make this fraction 0 is numerator being 0. A denominator equaling 0 will make it undefined. It is important, but it wasn't in the first one, it's in the second one. When x equals 0, the denominator will equal 0, and it will make the whole thing undefined. So, of course, you said that on purpose, just so someone can say something. But please, please understand that when I'm looking at a fraction, which one, the numerator or denominator, which one affects which result? Very important. And it happens all the time. All the time. Don't feel it's just you in any way. That's why I'm making a point of this. That people swap the roles of the numerator and denominator. I can have a denominator. It doesn't matter. The answer will never be 0 until the numerator equals 0. Okay, so out of this, not much is coming, but I have one interesting point. X equal to 0. So I'll just mark that off. So my x values are split in 2. Okay, I have a third floating around, and I won't write the 1, of course, that's doing nothing. My cube root of x squared. So the pieces that I have to work with in the case of fraction powers of x look a little different, often. Not always, often. A third is always going to be positive. This is where I really like the cube root, the root version, which in this case is a cube root. It's going to be 0 when x is 0. Of course, this all combines to make the derivative. Because this piece features in the denominator, it makes the whole thing undefined, in this case, the derivative. Which side do I want to do first? Maybe the left side of the interval. I need to fill in pluses and minuses. To the left of 0 for x, I have negative x values. But when I plug it in there, I work inside out. I square, making it positive. Cube root of a positive number is positive. For positive x values, of course, it's going to be positive. So you see here, it's not always going to go negative to positive. Sometimes it's the same, sometimes it's flipped. You need to think about the piece that you are working with. And I see here, 2 positives will make a positive, 2 positives will make a positive. So it looks like nothing is happening. I have an upslope, bad times, upslope. Okay, this example, we don't need the fraction powers of x to be complicated to show us its complications, I'll call it. So now my sentence. Again, my sentence refers to the original, and this time it's called y, is increasing on what? Do I say this? Sorry, that was an ugly infinity. I apologize. Or do I say this? It's one of them. Which one is it? We have 2 minutes. But don't take 2 minutes to respond. This is our last little bit for today. And then we'll do another example and another one and move on and just take as long as we need to take. We can't skip these things. They're too important because I can't trust that you're going to discover all of these little things, and when you encounter that in a problem you're doing on your own, are you going to know what it all means? No, that's my job. That's why I'm here. I agree it's one of them. This is the first or the second. And this is where I need to train myself to remember all conclusions I am making is in regards to the original function. And you see here, even though the derivative is undefined at 0, which clearly it is, the original function is defined everywhere. What is the cube root of 0? It's 0. The original function has no problems. It has no asymptotes, it has no holes, it has nothing. It's perfect. It's actually the y-intercept is at x equal to 0. Let's get a picture of the graph that we would have at the end of step 2. We would have a y-intercept right there at 0. We would know it's going up, we would know it's going down. That's all we know. There's a point. It's all good. And this is a good example to show that just because the derivative is unhappy with an x value doesn't mean the function is unhappy. Function is perfectly happy. Now, this is a first example where I haven't seen something like this before. What on earth is then happening? I have a graph throughout, one piece, nothing strange is happening, yet the derivative is undefined. If I think about straight lines, almost all straight lines have a slope. Almost all straight lines fit y equals mx plus b, except one. Except one straight line does not have a slope. Its slope is undefined. It's the vertical straight line. So if there is a graph here, there's a tangent line, yet there is no slope. The only way that can happen is if I have a vertical tangent line, which is what's happening here. And very often with fraction powers of x, I have a vertical tangent line that needed to curve away a little bit. So this I have not seen before. If I have a function that's defined everywhere, yet the derivative doesn't exist, vertical tangent line. Vertical tangent. And I get these interesting things when I look at the fraction powers of x type of function. But I mean, it's okay. I need to see it in an example, maybe a couple, to get more comfortable with it. The first one's never going to be super comfortable. That's okay. That's okay. It's still always increasing. Compare any 2 points. Compare the y value. Always going up. It's always going up. It's just super steep. As steep as you can imagine for a moment. And then it flattens a little bit again. All increasing. And I'm building that experience slowly by looking at more and more examples. Let's make it a little bit more interesting. Not super interesting. A little bit. And we will see these functions again. Let's look at this guy. X minus 1 all to the power of 2/3. Let me just make it clear what my denominator is. It is a 3. All right. So now I have no idea what this graph looks like. I see a fraction power. Yeah, the fact that it's x minus 1 in the bracket just means there's a little shift happening. It's not really a different type of function. So I am going to find the derivative. And that's going to be a chain rule. It's something to the power of 2/3. So the first part of the chain rule will be 2/3 times the something to the power 1 less, which will be negative 1/3, times, says the chain rule, by the derivative of that inside something, which is 1. Now for the purposes of moving forward into my table and seeing what is happening with this derivative, I do want to clean this up as much as I can. For me, personal preference is to get rid of the negative exponent. So I will move it to the bottom. And perhaps I want to just remind myself that whenever I need to see it this way, this is just the cube root. Maybe that helps me, but either one of these I like before I move forward. So I have a reason to simplify because it's going to make my life easier for my upcoming table. So I'll do it over here. There are 2 things that I want to check. I want to check when is the derivative equal to 0 and when is the derivative undefined. Always going to be those 2 things, no more, no less. And the more we see them, the easier they will get. So I see that in my numerator, I only have 2/3. There are no x's, and only the numerator can make the function 0. So that's going to be a never. I do see I have something in my denominator. When x is equal to 1, I will get a 0, making the whole thing undefined. All right. So we will list all the numbers we get out of these 2 checks. In this case, there's only 1. And I'm going to list all the pieces that I see. I see a 2/3 and I see a cube root of x minus 1. Together, they combine by way of multiplication and division to give me my derivative function. Now 2/3 is always positive. Not a problem there. But I don't want to miss anything here. If that 2/3 was a negative 2/3, then it plays a bigger role. So I just get into the habit of listing absolutely everything I see in my function. Cube root of x minus 1 is 0 when x is 1, and because it's in the denominator, we've said it makes the derivative undefined. Okay. Now, this looks perhaps a little bit uncomfortable. To the left of 1 is this positive or negative. A shortcut that you can take to make it easier is I can take a representative number inside this interval. It's 0, so it's inside this interval. Plug in that number, but then I get cube root of negative 1, which is negative, and it's going to be negative for all of them, as long as I've listed everything that I got from these checks. And I've split up my table correctly. You can take a representative number, and whatever it does for that piece, the whole section will do the same. So I'll put a representative number of 2, something easy I can easily work with in my head. 2 minus 1 is 1, cube root of 1, positive. So that's one thing you can do if the component that you're looking at is a little bit less familiar. Now, a positive and a negative will always make a negative. Two positives will always make a positive. So my slope lines are going down, bad things happening, going up. So it's not a little cup that it's making in the conventional sense, because I do not have, I'll emphasize it here, there's no horizontal tangent line here. That would be when the derivative is 0, and that's not the case here. So I do go from downhill to uphill, but let's see what's happening here. Let me set up a graph so I can at least visualize something. So, of course, we're just doing step 3. And again, that is not sufficient to clearly know what the graph looks like. If I did step 1 and 2, I would see that it goes up on either side. There is a y-intercept. Oopsie. What's my y? What's my y-intercept here? It's going to be 1, right? I don't know where these lines are coming from. Y-intercept of 1. Let's put it over there. And obviously something is happening at 1. Something unpleasant is happening at 1. The derivative is undefined. Yet, because I can see this as the cube root of x minus 1 squared, cube root is defined everywhere, this function is defined for all x values. So the function has no problem with any x values. It's the derivative that has a problem. And when I have a situation like that, for our level of functions, that's when I get the vertical tangent line, that there is a tangent line at 1. The only way the derivative cannot exist at the same time is if it's a vertical tangent line. Now I'm coming down and I'm going up. I'll give you a little, I guess, preview. You are not expected to know what this looks like at this stage, because we don't have all the steps. We're just doing one step. I make a sharp point there. Vertical tangent line. Vertical tangent line. The more I see this, the better it'll get. I have a function value. It's defined there. The derivative is undefined. Has to be a vertical tangent line. Okay, but looking at this function, if I did step 1, identifying it as the fraction power of x type, I know from the start to watch out for vertical tangent lines. And when I have all the steps, all the pieces will hint at that shape. So the more I do it, the better it's going to get. Slow and steady. All right. Again, feel free to interrupt me if you have any questions. like always. Okay, let's do an example with an exponential component. Those are probably my favorites because when I take the derivative, they're not going to be super difficult. I'm sticking to the natural exponential function. But at the same time, they give me more interesting examples than just polynomial or rational function, while not being too extreme with vertical tangent lines and difficult things like that. So I would do steps 1 and 2 maybe, or maybe a test question could just be find the intervals where it's increasing, decreasing. And I just realized we never wrote down our sentences here. I got a little excited about the graph. I'm sorry. We should write our sentences. Let's at least see the table here. Okay, so I can say here y, whoops, not eraser mode. You should always write your sentences. Y is increasing on 1 to infinity. Do I include 1 or not? Do I put a square bracket or a round bracket? I always want to make these intervals as big as possible. Even though the derivative is not defined, there is a point there. The graph is defined there. Include it. It's not about the derivative. It's about the function itself. And then y is decreasing on negative infinity to 1. Include it. If I compare any 2 points and 1 happens to be one of those 2 points, it's going down. It's part of that interval. So always write these sentences. I just forgot. Okay. All right. So before I move on to this example, actually, I want to classify these points that keep coming up that are interesting. When I look at this first example, I checked where is the derivative 0, where is the derivative undefined. We got an x equal to 1 coming out of that. And what I get here is a point where things are changing. It's going downhill to uphill. There's a turning point. It's an interesting point in the graph. We're going to call that a critical point. It's really critical to the property of the graph, to the features of the graph, to the type of graph that I see. Critical point is going to be 1, 0, the point 1, 0. Or I can say critical point at x equal to 1. Okay. Now, I don't have my other examples with me, but we saw other points coming out of this check, derivative equals 0, derivative undefined, and we'll call them critical points. So let me just classify that. A critical point, I won't be too fancy with this definition, is going to be when my function, my derivative is equal to 0 or my derivative is undefined. Undefined. All right, so those two situations could give me a critical point. And I always check those two. And, capital and, I have to have a point. It's critical, it's important for my table out of these two checks. And it has to be a point. Sorry, there's a question. I'm just not sure. Let's go back to the previous example. What was our function? You always have to check the function. And if that function is defined at the point, only then can we include it. But let me know what your question is. Hello?
Oh, sorry. Sorry. Yeah, so in the last example, the derivative was not defined in zero, right? But we didn't include that in the
So are we
example.
looking at this function,
No,
cube root of x minus 1 squared?
no, it's a
Not the
y to
function.
the one third. The last example.
Y to the 1/3. This was our last example, wasn't it?
Um, which one?
The x minus 1 to the 2/3. The derivative. Yeah, I'm just not sure which example you're looking at here. We did the cube root of x as our first example, and then we did this one.
Oh yeah, that one. Cube root of x. Yeah,
Or
that
the
one.
very first one, then, not the last example.
Yep.
Okay, so the first example.
Uh-huh.
All right. So there we find 0 as, I'll call it the potential critical point. It comes out of the check where the derivative, equals 0 or undefined. I get x equal to 0 is the only thing that comes out of that. I don't know if it's a critical point yet. Regardless, it goes into my table. So then it goes into my table. I see that the derivative is undefined at 0 because it makes the denominator 0.
Yep.
But that doesn't decide if it's a critical point or not. I have to look at, can I plug x into the original function? What does that do to the original function? And the original function is cube root of x.
Okay.
And I can plug in 0 because the cube root of 0 is 0. There's no denominator in the original function. The derivative and the power rule created that denominator. The original function has no problem at x equal to 0. Where's that graph? I find the graph. Where are you, graph? Come to me. There it is. Original function is one continuous line, nothing. There's a y value for every x value. The y value is 0 when x is 0. So my requirements for a critical point is that it comes out of that check of the derivative, but the original function has to be defined. And in this case, it is. The derivative may or may not be defined. I really don't care. In
So
terms of
then,
classifying it as a critical point, it has no role, whether it exists or not. It's the original function that I'm trying to graph. So the original function has to have a point there for me to call it a critical point. Sorry,
okay.
interrupted. Go.
So then zero is included.
0 is included. So when I write my sentence, the function is increasing on. I don't exclude 0 with two separate intervals. I go over 0 because throughout the function is included.
Yeah, I
There's no
guess I got
jump in the graph. It's one continuous graph. If there was a vertical asymptote and in order to draw my graph, I have to draw it, lift my pen over the vertical asymptote and continue drawing, then I have to exclude 0 because there is no point where there's no y value at x equal to 0. But that's not the case here. It's one continuous line throughout. Yes, interesting things happen at 0, but in terms of a graph existing there, it's totally fine. I graph through, I draw it. Yeah, I go a little vertical, but I continue drawing. I never lift my pen. There is a graph, so to speak, for all x values throughout. So I don't exclude 0 then. I would only exclude it if I lift my pen over it when I draw the graph. And that's not
yeah,
what happens here, right?
yeah, I get it now. I guess I just got confused because of the first sentence, but now I get it.
Yeah, no, I mean, this is brand new. So totally fine. Totally fine. And then we look at a slight variation of that. Now, When I get to the derivative, I certainly want to look at the exponential version, but I'm trying to find, when did I write this down? When it's convenient to sort of think about the function and getting y values, then the root version is sometimes beneficial. So I want to be able to flip back and forth between the root version and the exponential version. So when I have this function, I'm trying to find where we were now. This function. Again, the original function is defined everywhere. Cube root, defined everywhere. Square roots won't be. Cube root's always going to be good. But when I look at the derivative, sure, it has a denominator. It has some problems. But that doesn't, I use that to find the key, or let's say, to find the potential critical points. The x value comes out as 1, derivative, because the derivative is unhappy there. But whether it exists or not doesn't matter. I look at the original function, and the original function is defined at x equal to 1, which would make that a critical point. The original function is defined everywhere. Now, I don't remember where we were. Let's graph it like that. So this one looks a little different because the numbers that feature in the exponent is different. This one as well. I'll go through, when I graph this function, I never lift my pen. I go all the way. Interesting things that I'm doing, sure, but I never lift my pen. I never jump over 0, x equal to 1. I go through it, the y value is 0 at that point. There's no jump that I have to lift my pen. So when I write down my sentences, I don't remember where we were. When I write down my sentences, I have to include that regardless of what the derivative is doing. I'm trying to make a statement about the original function. I'm trying to draw the original function. So everything has to sort of be referred back to that function. I have to check that function because the derivative properties make the derivative look potentially very different than the original function. I use the derivative to find those key x values, but I'm always trying to say stuff about the original. The derivative is just a means to an end. I'm not making statements about the derivative. It's just being used to find those key x values in the original function. It takes a while. It takes a while. We'll get used to it, especially when we get to the next step. You'll see the same kinds of things pop up again and again. But no, let me know. We have time. Let me know if you have any questions. Type it, speak it. It's all good. Let's continue for now. Know from the start to watch out for vertical tangent lines. And when I have all the steps, all the pieces will hint at that shape. So the more I do it, the better it's going to get. Slow and steady. All right. Again, feel free to interrupt me if you have any questions, like always. Okay, let's do an example with an exponential component. Those are probably my favorites because when I take the derivative, they're not going to be super difficult. I'm sticking to the natural exponential function. But at the same time, they give me more interesting examples than just polynomial or rational function, while not being too extreme with vertical tangent lines and difficult things like that. So I would do steps 1 and 2 maybe, or maybe a test question could just be find the intervals where it's increasing, decreasing. And I just realized we never wrote down our sentences here. I got a little excited about the graph. I'm sorry. We should write our sentences. Let's at least see the table here. Okay, so I can say here y, whoops, not eraser mode. You should always write your sentences. Y is increasing on 1 to infinity. Do I include 1 or not? Do I put a square bracket or a round bracket? I always want to make these intervals as big as possible. even though the derivative is not defined, there is a point there. The graph is defined there. Include it. It's not about the derivative. It's about the function itself. And then y is decreasing on negative infinity to 1. Include it. By comparing 2 points, and 1 happens to be one of those 2 points, it's going down. It's part of that interval. So always write these sentences. I just forgot. Okay. All right. So before I move on to this example, actually, I want to classify these points that keep coming up that are interesting. When I look at this first example, I checked where is the derivative 0, where is the derivative undefined. We got an x equal to 1 coming out of that. And what I get here is a point where things are changing. It's going downhill to uphill. There's a turning point. It's an interesting point in the graph. We're going to call that a critical point. It's really critical to the property of the graph, to the features of the graph, to the type of graph that I see. Critical point is going to be 1, 0, the point 1, 0. Or I can say critical point at x equal to 1. Okay. Now, I don't have my other examples with me, but we saw other points coming out of this check, derivative equals 0, derivative undefined, and we'll call them critical points. So let me just classify that. A critical point, I won't be too fancy with this definition, is going to be when my function, my derivative is equal to 0 or my derivative is undefined. Undefined. All right, so those two situations could give me a critical point. And I always check those two. And, capital and, I have to have a point. It's critical, it's important for my table out of these two checks. And it has to be a point, meaning my function is defined there. There has to be a point there. Now, if you think back to, let me just go quickly find that example that we did, the rational function one. We did this. You can look back on your notes. We did that yesterday. We found the derivative to be 2 over x plus 1. Everything's squared there. So when we then did our derivative equal to 0, we found never. Our derivative undefined. Yes, that was when x was equal to negative 1. This, however, is not a critical point because the function is not defined at x equal to negative 1. The original function has a problem there as well. It was a vertical asymptote, right? Quickly graph this. We had a vertical asymptote at negative 1. Horizontal one doesn't actually matter right now. We had a fundamental problem at negative 1. It jumps over. There is no point at x equal to negative 1. So it can't be classified as a critical point. It has to be critical, but it has to be a point for me to call it a critical point. Okay, so let's keep that in mind as we look at this function, and then we will see what the critical points are, if there are any. Okay. So I'm doing step 3. Step 3. Derivative is what I need to find. Clearly the product rule. Derivative of the first times the second plus the first times the derivative of the second. Now I want to clean this up. I want to know, moving forward, what is the best version I can get? Well, I'm going to take an e to the x out, and I'll have an x plus 1 or a 1 plus x left. That's the best I can make it look. I have a positive exponent there, so it stays above the line. Then I want to check, where is the derivative 0? Where is the derivative undefined? Always those two things, no more, no less. So now I have the luxury that I don't have a fraction to worry about. So it's going to be when either one of these two equals 0, right? It's going to be when either e to the x equals 0 or when x plus 1 equals 0. So I have from the second one, I certainly have a negative 1 for x. When is e to the x equal to 0? Is my question to you. When is e to the x equal to 0? If I have a product, then I have to check each one of those factors, right? And whenever any one of them equals 0, that's an x value that I need to list. And I need to make sure I have all the x values. If I miss one, my table is going to be messed up. Everything is going to be messed up. I need to not miss one. So I get negative 1 from the second, x plus 1, obviously. But the other one, e to the x equal to 0, is also one that I need to check. But I know what my e to the x graph looks like, and I know it's always above the x-axis. It's never going to touch. There are none. So negative 1 is the only point. But you need to know. So never is the answer for e to the x equal to 0, and therefore I only have the negative 1. Picture the graph, read it off. It's all there. And undefined, all of these things are defined. I'm not dividing by 0. It's all good. So that's a never. So the only point of interest in terms of increasing, decreasing behavior is x equal to negative 1. I'll call this my potential critical point because I've done half of the check. I've done the top part. I need to make sure it's actually defined there. So we can check at this stage, or I'd like to do it after actually, but it doesn't really matter. I've cleaned up my derivative. I have a potential critical point. I'll check the function later when I write my sentences. I've sort of got into the habit of doing it everything at the end. I don't know why my line is so long, because only negative 1 is a point of interest here. So everything I list, e to the x, x plus 1, and they together give me the derivative. It has to be multiplication or division. I could not have taken the top, which had 2 terms. Okay, e to the x, again, I read it off my graph. It's always positive. X plus 1 is 0 when x is negative 1. It's in multiplication, going to make the derivative 0. X plus 1, check it. It's going to go negative to positive. So I have a positive and a negative, gives me a negative answer. Positive, positive gives me a positive answer. So my slope lines are going to go down, horizontal tangent, up. So a nice little cup shape that I get there. I don't know what my lines were doing there. Oh, there was one cup there. Whee! There we go. All right. Well, let's write our sentences. F is increasing on negative 1 to infinity. Do I include negative 1? Yes, I do. Because I have a y value, plug it in. I can get a y value. Now I don't really care right now what the y value is. The important thing is that I get it. So y value exists. This function is defined for all x, because why not? E to the x is defined everywhere. X, no, no division by anything. There's no problem at all. I can maybe write without. I just don't want a decimal number here. It's gonna be uh, negative e to the negative 1, right? Whatever negative 1 over e is. Who cares? It exists. That's the only thing that's important. And f is decreasing on negative infinity to negative 1. Critical point? Yes. It's at x equal to negative 1 because it came out of my check of the derivative and there's an actual y value. There is a point. Critical point. All right. So hopefully with these examples, it covers enough for now. When we move on to the next step next time, you'll see a lot of the thinking copies itself. It's the same. It's not exactly the same, but it looks very similar. So it adds to the practice for this section in a way as well. Different, but very similar. And slowly we're going through all the steps and uh, make sure you practice each of the steps as we go. We finished the increasing decreasing step, which I'll call step 3, just based on our breakdown. So you can practice all of that step 3 problems in the problem book, depending on how much time you have. And let me know if you have any questions. Are there any thoughts that you want to share right now, though? All right. Then that will be the end for today. Just takes a little bit of practice and you'll get used to it. Make sure you can handle each of the 5 types of functions and there will be no surprises in any test. All right, until next time. Thank you.